you crash
didn't
them
put it
together.
so much that way.
Yeah, yeah.
For him, it was a matter of if you take a mass, any mass, and you accelerate it to closer and closer to the speed of light, what you're going to see is the apparent mass of the object increases. The relativistic mass
Right.
of the object increases. So then we saw that when we started actually, well, using cyclotrons to accelerate things to close to the speed of light.
That's really cool. Okay, so just to clarify them, so we've got three. Were there any more? Sorry, before I. Were there any more?
So we had time contraction, we had
Time
mass
contraction.
energy equivalence,
The speed of light being the same.
and the speed of light. So those are really the key things for special relativity.
Okay.
Those are the big factors that we needed to deal with.
Oh, Steve said light deflection. Was that part of?
That's general.
That's general. Okay.
Getting there.
All right, so we'll move on to general. Okay, so that wrapped up special relative. Sorry, let me say that again.
Okay.
Okay, so that wraps up the predictions that he made for special relativity. But then, really, his greatest theory, the one that blew everyone's minds, was general relativity. And this is what I said at the beginning of the show, that he made some predictions with general relativity that astronomers haven't had the capability to test until just within the last 5 years. It's crazy.
And we're still working at getting things totally at the level where everyone's like, yeah, okay, you proved it.
Einstein was still right. Okay, so let's run through some of the predictions that he made and try to put them in order of when they were able to do experiments to prove that they were true.
Well, the
relativity.
easiest one in some ways was the perihelion precession of Mercury.
What?
Yeah, I know, lots of fancy words there.
Yeah,
so
fancy astronomy words. So what was going on with Mercury?
So with any orbiting object, according to Kepler and later Newton, orbits are ellipses, flattened circles, two perfect circles somewhere in there, that have at the foci of the ellipse, Google ellipse, you'll see what I mean, you have the star, the planet, whatever's being orbited, and the perihelion is the point of closest approach to the sun. So as Mercury goes around on its elliptical orbit around the sun, it has a closest approach, it has a furthest approach. Now, if you were to erase everything else from the solar system, so you have no other planets, if you were to make the sun a perfect circle, then Mercury's orbit would just happily be exactly the same orientation for all of time. Now, the truth is, sun's not a perfect circle. It's a bit squished around the middle. It's oblate is the fancy word. And so that oblateness causes some effects on the orbit, makes the orbit slowly change over time. Fact is, we do have 7 other planets and a bunch of other rocks and icy bodies. And over time, those rocks and icy bodies and other planets, for the most part, have effects on Mercury. But when you add up all these other effects and you look at Mercury's orbit, Mercury's point of closest approach to the sun is slowly moving over time in a way that all those other effects can't take account of. It's precessing like the top of a spinning top at a rate that's faster than would be expected. And when Einstein integrated gravity into his theory of relativity, he found that precession was predicted, and the thing was is he could actually predict how much the precession would be at a level that was greater accuracy than they'd really done in their measurements at that point. And sure enough, as we've gotten more and more accurate measurements, we're able to find, wow, he nailed it. He was exactly right in being able to tell us where we can find Mercury at any given moment as it precesses around the sun.
And that is really just like the perfect theory that you take something that astronomers have been puzzling about for decades and come up with the math and the theory and go, oh, if you run my math, this will explain what you're looking for. and that's just getting out of the gate. That's as
Yeah.
just to warm up the engines. I'm going to explain a bunch of the unsolved mysteries that you've got in front of you, and now
Right.
here's a bunch of crazy predictions that didn't even occur to you that I'm about to make about the universe. So, feel free to go out and prove that those are true too. So, so right, that precession of Mercury, perfect. So what was next?
Well, and the thing that went in with the precession of Mercury is the exact same physics that applies to Mercury going around the sun applies to binary stars, applies to binary pulsar systems. And we're seeing this in dramatic ways as we look at higher mass compact objects over time. So there's a pulsar that we see, actually, its precession is 4.2 degrees per year. So this is like high-speed precession with high-mass objects. Now, the next big thing of evidence that he came up with was the deflection of light by gravitationally massive objects. So starlight getting bent around the sun. And I have to admit, I and many other people are guilty of saying, and Eddington went out and showed this when he looked at the 1919 solar eclipse. And yeah, Eddington did see light bending. But the thing is, people have argued over whether or not that's sufficient evidence ever since. Because, well, even Newton predicted that light would bend. It's the amount that it would bend. And when you look at the errors in Eddington's measurements, it's just not quite entirely conclusive. And so people are still, this is the one piece of evidence that people are still going, okay, is it fully conclusive?
Mm-hmm.
And we look at things like Einstein rings, where we don't know the masses precisely, but we're starting to get as precise as you could hope for, not by looking at the optical light of starlight, but rather by looking at background quasars using radio astronomy to get highly precise measurements. And with our most sophisticated radio telescopes, we're just starting to be able to say the error bars are small enough that, yes, the amount of deflection of light by massive objects does conclusively say Einstein was right.
Right, and so this was this theory, right, that he said that we should look at gravity not as some kind of attractive force between objects with mass, that we should see it as a bending of the very fabric of the universe, that in fact it's this depression in the space-time, and so both massive objects and energy will follow the bended curves in the space-time caused by these massive objects, and this bending of the light that we see matches this prediction exactly. And as you said, they're still testing it out to higher and higher degrees of accuracy. Why use a star going around the sun? Let's use a distant quasar that's been traveling for 12 billion years.
Well, you can also just get more precise measurements that way because of the radio light. It's just easier to use radio, rather. Yeah. And quasars aren't moving. The problem with stars is they're orbiting the same galaxy we're orbiting. And so it's the quasars in the background that are the most non-moving things in the sky.
Right. Okay, cool. So next.
Gravitational redshift.
Gravitational redshift. So what is that?
This is the idea that light, as it climbs out of a gravity well, light as it shines perpendicular to the surface of the Earth, of a black hole, of a white dwarf, of anything with gravity, will lose energy as it climbs. So it climbs at the speed of light. Light travels at the speed of light for all observers. But no one ever said it wasn't going to change colors in the process. So sunlight, as it falls to Earth, gets blue shifted, and sunlight as it climbs out of the sun's gravity well gets red shifted. And that's all well and good, but it's kind of hard to measure. So the key experiment was actually done at Harvard, and the place where it was done still exists. And if you go wandering the Harvard physics department with the right person in hand, they'll point it out to you. There's a tower there where they shined, or more or less emitted, gamma ray energy up the tower, and they measured the slight change in color of that light that was a result of climbing up the Earth's gravity well. And this is something that what's neat about it is one of the problems with light getting off of a black hole is it not only can't go fast enough, but it actually gets redshifted into oblivion.
Right, and so you can imagine now astronomers have demonstrated this in all kinds of different ways. I mean, they demonstrate it from light coming from different quasars, light coming from planets, from stars, from neutron stars, and all the different kinds of radiation, and they're able to make these predictions again and again and again. It's awesome. So that's a good one.
Yeah. So the more high mass objects we look at, the more we're able to see that this is really going on out there.
Really cool. Okay, so that's 3 so far. Any more?
Yeah. So so then we have frame dragging, which is one of my favorite ones.
Mm-hmm.
So this is the idea that a rotating body actually rotates the space-time continuum around it, and that the way time passes, the way your energy changes, depending on which direction you're going around an object, is measurable in terms of there's differences depending on the direction you go in. So the gravity probe B is actually the way we finally said, yes, there is frame dragging. There'd been earlier experiments. We launched the Lagos satellite looking to try and measure it using that. Wasn't entirely conclusive. We'd seen some evidence from the Mars Global Surveyor as it orbited Mars. But it was finally when we launched Gravity Probe B with its extremely precisely made balls in its gyroscope that we were able to, by looking at how over time those spinning gyroscopic balls changed, we were able to see, yes, the changes are what was predicted by frame dragging. This is just one of those awesome things that we have to take into account when we measure things. They actually did it relative to the star IM Pegasus. They measured the alignment of the gyroscopes relative to a star, and it builds up over time. So what they were able to see was a change that added up to 37 milliarcseconds over the period of the experiment.
So just to understand this correctly, you've got the satellite, you launch it in space,
Mm-hmm.
you spin up these gyroscopes so that they are perfectly aligned with this star,
Mm-hmm.
and then you have the spacecraft going around the Earth in such a way that if there was no such thing as frame dragging, then you could go a million years and these gyros would still be perfectly lined up with this star. But instead, because the Gravity Probe B spacecraft is moving through the Earth's gravity field and the Earth is turning, you get this change in the orientation that comes purely from the way the Earth's gravity is warping space-time. Did I get that right?
Yeah. Now, it's not that you have the pole of